Well, that's the problem. The James Webb Space Telescope is upsetting the apple cart. All of a sudden, we realize that we may have to rewrite all the textbooks about the beginning of the universe.
When the James Webb Space Telescope opened its mirrors to the deep universe.
As a member of the James Webb Space mission, I asked her if it was worth the effort.
Scientists expected clearer views of familiar cosmic history. Instead, it returned images that broke the script of everything we thought we understood. Webb found a galaxy that should not exist, a massive and mature system shining at a time when the universe should have been dark and chaotic.
You know, the ingredients of the galaxy and the universe, and we on Earth are just a tiny part of that.
The deeper Webb looked, the stranger the universe became, as if reality was hiding a second layer. Something in the distant universe was breaking the rules so much that even physicists could not explain the data. The first impossible galaxy.
It occurs to me you're the first two people to see these images in human history.
When the James Webb Space Telescope captured the light of a distant object labeled as a young galaxy, most astronomers expected the usual signs of early cosmic growth. They expected half-formed clusters, chaotic clouds of gas, and the rough beginnings of a structure still finding its shape. Instead, the telescope revealed something that stunned the scientific community. The galaxy existed just 290 million years after the Big Bang, which should have been far too early for any fully formed system to appear in the universe. This discovery went against the most trusted models of galaxy formation. According to standard cosmology, the universe in that period was still cooling from its violent beginning. Matter had only recently started clumping together. There should not have been enough time, pressure, or stable regions of space for a large, bright galaxy to form and shine with such intensity. Yet the data showed a structure that looked mature and complete, almost as if it had skipped the growth stages entirely. What made the discovery even harder to explain was the extreme brightness of the object. The galaxy emitted light far stronger than predicted for its age. Early galaxies normally release dim, scattered light because their stars form slowly and unevenly. What Webb detected was the opposite. The entire system glowed with a clean, steady brightness, suggesting the presence of a large population of stars that were already stable and well-developed. This was the first sign that something about the object defied expectations. Deep spectral scans revealed another surprise. Instead of the young, unstable stars expected from that cosmic period, the galaxy contained older star populations with clear chemical signatures. These stars should have taken hundreds of millions of extra years to form. Their presence created a direct challenge to the accepted timeline of star development. If these stars were truly as mature as their signals indicated, then our current understanding of early star cycles might be incomplete. The galaxy also lacked the heavy fields of gas and dust that should have surrounded such a young system. In the early universe, galaxies were messy and unstable because they were constantly gathering leftover matter. This object had almost no trace of that debris. It looked as if it had used every available particle to create stars, leaving behind nothing but clean starlight. That level of efficiency suggested a 100% gas-to-star conversion rate, something no natural process has ever achieved in modern observations. Even the most active starburst galaxies today cannot convert more than a fraction of their gas into stars. The shock did not end with one discovery. Once the team pushed the search deeper into the same region of the sky, the telescope found dozens more galaxies showing the same impossible features. These structures were too big, too bright, and too organized for the time period they belonged to. Internal reports began describing them as foreign structures because they did not behave like anything predicted by known physics. As astronomers examined the growing pile of data, they realized they were not looking at isolated anomalies. They were staring at a pattern that carried consequences for the entire story of the universe. A universe that should not look like this. As researchers continued to sort through Webb's readings, another set of signals appeared that pushed the mystery far beyond the discovery of early galaxies. These signals came from positions that should lie outside the Hubble sphere, which is the boundary where galaxies move away from us faster than light because of the expansion of space. According to established physics, light from beyond that boundary should never reach Earth. It should stretch endlessly and fade before it has any chance of crossing the vast cosmic distance. Yet Webb recorded clear signatures that traced back to regions where light should be forever trapped away from us. This finding raised immediate concern because it hinted that something fundamental about the behavior of space-time at extreme scales might be different from what the standard model predicts. The equations describing cosmic expansion were built to explain why distant objects appear dimmer and further apart as the universe grows. Webb's detections suggested there might be pockets of space where these rules break down or behave differently. If light from beyond the Hubble sphere is reaching us, the boundary might not be as strict as scientists once believed. This forced cosmologists to consider the possibility that space does not expand evenly in all directions. When more data came in, several physicists took notice. They began questioning the long-accepted idea that the universe had a single explosive beginning that created all matter, time, and energy in one moment. The discovery of fully formed galaxies almost at the dawn of time had already cast doubt on the early timeline. Now, signals arriving from beyond the supposed limits of the observable universe added even more uncertainty. If these signals were genuine, they might point to an older or differently organized cosmos than the one described by the traditional Big Bang model. One possible explanation suggested that the early universe experienced phases of expansion that do not match the simple story taught today. In this idea, the universe may have grown unevenly or paused between stages, which could create strange distortions in how light travels across great distances. Another group proposed a timeline error, meaning that the structure of the universe formed much earlier than our models predict. If the first galaxies are older than expected, it would shift the entire cosmic timeline. A more speculative idea involved a possible fracture zone in spacetime. This concept describes a boundary where two cosmological domains overlap or press against each other. The signals detected by Webb might be crossing through this boundary, giving us a glimpse into a region of space that normally stays hidden. Although this idea has no confirmed evidence, it fits the unusual behavior of the signals and explains why the light seems to come from unreachable zones. These findings forced cosmologists to rethink the idea that the universe expands in a simple, smooth pattern. Instead, it might behave like a layered or uneven system with subtle complexities that were invisible to previous telescopes. As timelines unraveled and boundaries blurred, Webb began picking up patterns even stranger, buried deep within the background noise. Signals that should not exist. While astronomers were still arguing about early galaxies and unreachable regions, Webb recorded something even harder to explain. Deep within the faint hum of the cosmic background, the telescope detected a soft, rhythmic oscillation. The signal repeated at precise intervals, so regularly that the team could predict the next pulse before it arrived. This strange frequency became known as the heartbeat beyond time, because it looked like a steady cosmic pulse, hidden underneath all other noise in the universe. At first, many suspected it was a calibration glitch or interference from Webb's instruments, but repeated checks showed the pattern came from deep space. Scientists pulled the pulses apart and found that the intervals matched known mathematical ratios, including harmonic sequences that appear in fields like quantum systems and wave physics. A few researchers argued this could be a natural resonance caused by the shape or density of the universe itself. Space can vibrate under certain conditions, just like a stretched surface can form repeating ripples. Yet others pointed out that the precision was far too clean. Natural processes usually show slight variation, but this signal remained exact down to the smallest measurable unit. That level of stability made some consider the possibility of an encoded structure or a pattern created by something unknown.
Has no substitute. There's no other way to get at this scientific discoveries that it'll make.
As this debate grew, Webb recorded another strange feature in the distant universe. Several far-off galaxies showed strong gravitational lensing, meaning their gravity bent the light passing around them. This bending was far stronger than their visible mass could explain. Normally, dark matter accounts for this imbalance, but the distribution did not match any model or simulation. Instead of forming smooth halos around galaxies, the gravitational effect appeared in sharp patches, almost like invisible hands pressing down from above. Researchers began calling this phantom mass because it behaved like gravity from an unseen source that was not tied to regular matter or known dark matter fields.
Trouble is, infrared is invisible to the human eye.
This was not a single isolated case. Webb observed similar distortions across multiple regions. Each one suggested the presence of something heavy or influential in areas that showed no light, no dust, and no measurable particles. A few specialists propose that these distortions might come from higher dimensional effects, predicted by some versions of advanced physics. In these theories, Gravity can leak between dimensions, causing unexpected pressure in places where no matter exists. Another anomaly added to the confusion. One of Webb's instruments tracked a narrow light signature from the edge of the observable universe. For a brief time, the signature faded completely, almost as if it had disappeared behind something. Moments later, it returned with the exact same spectral fingerprint. This was unusual because light that travels across the universe normally stretches and changes in predictable ways. If a light beam returns unchanged, it suggests it bounced off a surface or boundary. Observatories around the world logged the recurrence and classified it as possible evidence of a closed or partially bounded cosmic system. This idea implies the universe might have an edge or a reflective layer, rather than being open and endless. The thought of a boundary sitting far beyond what we can normally see shook the scientific community, because such a structure is not part of any standard cosmological model. With anomalies building from every direction, theorists started proposing explanations that once sounded impossible. The mirror universe theory. As the strange data continued to pile up, one idea grew louder inside research groups. It suggested that our universe might not be alone. Instead, it could have a physical twin that developed beside ours and moved in the opposite direction of time. This idea is not new, but the recent findings from JWST gave it new life. Scientists noticed that some galaxies far from us had rotational patterns that refused to match expected behavior. They spun in ways that suggested the presence of a counteracting pull, almost like an unseen partner was influencing their motion from somewhere else.
And it doesn't look like an elliptical galaxy, and it doesn't look like a spiral galaxy.
Teams studying high-energy particles found something even more unusual. They observed paired movements in separate regions of the sky that lined up with each other. The reactions were too synchronized to be simple coincidence. The data hinted that particles in our universe might be responding to changes inside a hidden environment that sits right beside ours, but cannot be seen. Researchers began calling it a shadow environment. This term helped describe a space that shares similarities with ours, but remains out of reach.
To enlarge the emissions of more than 3,000 previously hidden ancient galaxies.
Gravitational models added more weight to the idea. When scientists simulated the possible effects of an unseen universe that runs backward in time, the results showed subtle gravitational tugs on our universe. These tugs matched the strange distortions JWST had been recording. The phantom mass fields, which bent light without showing any visible object, could be the result of overlapping gravitational waves from a mirror realm. These waves would not be strong enough to pull stars or planets apart. They would only create slight but noticeable marks in the fabric of space, which is exactly what the telescope recorded. A separate team explored the behavior of light coming from distant objects. Some of the light that reached JWST seemed to have taken a path that did not match the surrounding space. It appeared as if the light crossed through an unseen region before reaching us. This led to the idea of a boundary zone. In theory, this zone could be a thin layer where both universes touch. If light slips through this shared border, it might carry mixed information from both sides. This could explain why a long-distance light signature vanished and then returned with the same exact spectral fingerprint. It behaved like a beam that hit a reflective surface at the edge of something large. Simulations that combined all these findings began producing even more intriguing results. When scientists added a mirror universe with opposite time flow into their models, impossible galaxies suddenly made sense. A twin universe could apply pressure on ours, speeding up the formation of early structures. The rhythmic heartbeat signal in the cosmic background also became easier to explain. It could be the result of synchronized activity between two cosmic realms that have been connected since the first moments of existence. The idea remains speculative, but it fits more of the data than expected, and that makes it hard for researchers to ignore. Another theory, however, challenges everything even more deeply.
That galaxy is about 5 billion light years away, so we're looking back in time by 5 billion years.
Signs of an interdimensional collision. A growing number of cosmologists believe the universe might be showing signs of something far more dramatic than a mirror realm. They argue that JWST may be catching the traces of two universes physically intersecting. This idea comes from a mix of strange data that refuses to sit quietly inside normal cosmology. When viewed together, the patterns form a picture that some scientists describe as the early stages of a cosmic intrusion event. The impossible galaxies found by JWST are at the center of this theory. They appear too large, too mature, and too organized for the era in which they seem to exist. Some researchers suggest these galaxies may not belong to our universe at all. Instead, they might be the last surviving structures of an older universe whose edges are drifting into our field of view. In this scenario, JWST is not seeing early cosmic history. It is seeing foreign material from a universe with a completely different lifespan.
And we find some enormously interesting things.
Phantom mass fields add more weight to this idea. These fields bend light in ways that suggest strong gravity, yet nothing visible produces that pull. The collision theory suggests these distortions may be gravitational scars. They would be left behind by massive objects that exist fully in another universe but only partially overlap with ours. Their presence would act like dents in space. These dents would cause light to bend incorrectly, creating the strange lensing effects JWST has recorded. The reflective edge signature may also fit into this model. In several readings, a distant light pattern vanished and then returned with the same spectral fingerprint. The event looked like a reflection, yet there is nothing in known cosmic structure that could cause such a clean return signal. Some theorists believe this might be a boundary membrane. In advanced brain collision models, universes exist on vast surfaces that sometimes brush or collide with each other. If two such surfaces touched, they could create a thin boundary that reflects or redirects light in unusual ways. The readings from JWST match this description in several ways. If universes overlap, the flow of time inside the mixed region becomes complicated. Timelines can fold, twist, or align in unexpected ways. This could allow older galaxies from a foreign universe to appear inside what we think is the early universe. They would seem to be in the past, even though they are not part of our own cosmic timeline. Some of the strongest hints appear in the cosmic microwave background. There are small data gaps and temperature irregularities that line up with predictions from dimensional intrusion models. These models show how an intersecting universe could leave faint marks across the entire sky. The shape and placement of these gaps look surprisingly close to the expected patterns. Together, these clues have led some researchers to suggest that we may not be living in a clean, isolated universe. Instead, we might be inside a mixed zone, where two realities are blending in imperfect and unstable ways. As if the theories have not made physicists even more confused, the next findings take the mystery even deeper. The hidden patterns in the data. As more scientists pored over the early JWST data, several research physicists, they were not troubled by one strange reading or one unusual galaxy. They were troubled by patterns that should not exist at all. The deeper they looked, the more the data began to feel like a puzzle that had been arranged by an invisible hand. Nothing outright broke the laws of physics, yet everything leaned in that direction. The first clue lay in the timestamp logs. Analysts noticed irregular shifts that did not match any known technical fault. The instruments were fine, and the observatory systems showed no errors.
Looking at a lot of objects in what seems like 2 dimensions, we've got a 3-dimensional view of the universe.
The shifts appeared as tiny jumps, almost like brief moments when the telescope experienced a slight stretch or compression in local spacetime. The logs suggested that the signals arriving from deep space were moving through regions where time itself might not flow in a steady way. Then came the strangest redshift readings. Some light sources displayed combinations that should cancel each other out. Instead, they behaved as if the light had passed through more than one spacetime framework. A few cosmologists proposed that JWST might be capturing photons that traveled across areas where spacetime layers overlap. In those regions, light could stretch and compress in inconsistent ways. This would produce redshift values that look impossible, yet remain consistent with a layered universe. Several distant galaxies added a deeper level of concern. When their star positions were mapped, the stars formed geometric patterns that resembled predicted layouts of a non-standard universe. These patterns were not exact, but the alignment was close enough to trouble researchers who had studied theoretical models of alternative cosmic structures. The galaxies looked like they belonged to a place governed by different physical rules. More unsettling were the repeating signals detected on opposite ends of the sky. These signals had the same structure, the same light curve, and nearly the same timing. They should have come from completely unrelated regions, yet they behaved like echoes from a single source that had been stretched or folded around the universe. This raised the possibility that spacetime might not be a smooth and open landscape. It might loop or fold in ways too large and too slow for humans to see directly. As researchers continued their comparisons, they found faint structures in JWST maps that matched old anomalies first noticed by the Hubble Space Telescope. At the time, these anomalies had been dismissed as noise or lensing errors. Now they formed a larger pattern when combined with newer data. It looked like a faint web stretching across the observable universe. Something had been there the entire time, just beneath the threshold of detection. Internal memos soon mentioned a quiet monitoring effort called Deep Field Integrity. This project tracked unexplained echoes, repeating light signatures, and irregular distortions. The goal was not to explain them, but to watch for shifts that might indicate a deeper instability in cosmic structure. Taken together, these findings suggest we are observing a universe far more layered, disturbed, and complex than any model has allowed. And all these threads converge into one final and unsettling possibility.
Really, for us to learn about the universe, we just have to look all around us. The universe, in fact, is our lab.
The universe behind the universe that physicists can't explain. As the evidence piled up, a few physicists began to share a quiet and unsettling idea. They believed the JWST might not be looking at the early universe at all. Instead, they suggested we could be observing something beneath it. In their view, the strange galaxies, the rhythmic pulses, the phantom mass, and the reflective boundary were not mistakes or coincidences. They were signs of another layer below the one we call our cosmos. This layer might have been present since the beginning, hidden in plain sight because no instrument before JWST had enough precision to reveal it.
That's baffling scientists because they don't fit in the normal sequence of the birth of a galaxy.
The thought began with the idea of a cosmic shell. According to some models, our universe might not be a boundless ocean of space. It might be a thin layer wrapped around a deeper structure. JWST has the ability to peer across immense distances with unmatched sensitivity. This raised the possibility that what appears to be light from the earliest moments of the universe is actually light filtering through a boundary. If this boundary has weaknesses, cracks, or thin points, JWST could accidentally glimpse structures from the deeper framework beneath.
The material in the galaxy is actually orbiting and falling into the galaxy itself.
This deeper framework offers a simple explanation for several anomalies. The impossible galaxies may not be galaxies from the early timeline. They may be fully formed systems from the layer below, seen through a weakened region of our cosmic shell. The rhythmic signal known as the heartbeat beyond time could be a periodic pulse generated by the deeper structure itself. The phantom mass fields might be gravitational pressure leaking upward from this older, heavier architecture. Even the reflective edge signature could be a faint glimmer bouncing off the internal surface of the shell.
How far back can you go to the origins of the universe?
If this is correct, then our universe is not a primary reality. It is a secondary layer shaped by a larger and older construction. This view changes the Big Bang from a universal beginning to a local event that only applies to our layer. The deeper structure may have its own history, time flow, and physical rules. It may be older than any timeline we can calculate. It may even be stable in a way our universe is not, which could explain why the anomalies appear more frequently at the far edges of our observable horizon.
30 years after the image, I still love to look at deep field.
The darkest implication is that we might be sitting close to the edge of this deeper system. When JWST looks into certain regions, it may be peering at weak points where the two layers interact. These interactions could create distortions, repeated signals, and mirrored patterns. They might also allow rare flashes of information to slip through. If the layers shift relative to each other, the cracks might widen or close without warning. To some physicists, this suggests we are watching a system we were never meant to see, not because it is forbidden, but because our place in the structure is too small to understand the full design. Thank you for staying with us to the end. Please subscribe to the channel for more amazing content like this.